I want to show you where the product rule comes from. I want to show you how it's derived so that you can see a proof for why it is what it is. Now, the derivation of a rule like this is fairly complicated. There's a couple of steps that might not seem obvious right away, and there's a lot of rearranging. So I hope that you are able to follow along a bit and see what's going on. But if it is complicated, I don't want you to be too concerned. Some of these sorts of proofs are really difficult for students who haven't seen them before. And so I just want to set everyone's mindset in the right place. This is not something I would ever ask you to do on a test or anything like that. I simply want to show you where the product rule comes from. So let's say that we want to take the derivative of the product of two functions. Let's say f of x times g of x. Now we can't use the product rule here because we're trying to show what the product rule is. We're basically trying to cook it from scratch, which means we have to use something else, and what we have is the limit definition of a derivative. So this is going to be the limit as h approaches 0 of our function evaluated at x plus h, which is going to be f of x plus h times g of x plus h, minus our function evaluated at x, f of x times g of x, all over h. Now, in mathematics, one thing that we sometimes do that you've probably done before, in fact, you've done in this class if you're one of my students and not some random person watching this on YouTube. If you are, welcome random person. But we will often, when we're trying to deal with limits, multiply the top and bottom of a fraction by the same thing so that we can maneuver things a bit. And what we're really doing is we're multiplying by a version of 1. Any fraction where the numerator and denominator are the same is equal to 1, and so we're just finding the right version of 1 to multiply by. And here we're going to do something similar but different. We need to find the right version of 0 to add, because we know if we add 0 to something, it does not change the value. And so we're going to add something in the numerator that's equal to 0, but what it's going to do is it's going to give us somewhere to go with these terms. So we've got our f of x plus h times g of x plus h. And between that and the other term, I want to add a couple of terms in that end up equaling 0 in the end. What we're going to do is we're going to first have a subtraction. We're going to subtract f of x times g of x plus h, and then we're going to add in f of x times g of x plus h, and we still have that last term that we have to keep in, the f of x times g of x. Now, this extra stuff that we've added in is effectively 0 because we've got a negative version of a term and a positive version of the term that are the same. So we've effectively added 0 into the numerator, but these extra terms are going to help us. I'm going to put that h in the denominator. These extra terms are going to help us get something that we can work with. All right, so what we're going to do, because we've got the limit of sums and differences and whatnot, we can take the limit of a sum and represent it as the sum of the limits. So long as those limits exist, we can split them up. So I'm going to split everything up along this plus sign in the middle into two different fractions, and I'm going to look at the limit of each of them. So we're going to look at the limit as h approaches 0 of that first half, which is going to be f of x plus h times g of x plus h minus f of x times g of x plus h all over h. And then we're going to add to that the other half. We're just splitting this up into two limits. The other one is f of x times g of x plus h minus f of x g of x all over h. All right. Now, in each of these, there is something that we can factor out of the numerator. All right. In this first one, there is a factor of g of x plus h in the numerator that we can factor out. So I'm going to write this as the limit as h approaches 0 of, and not only am I going to factor that out of the numerator, but I'm going to factor that out of the whole fraction. Instead of keeping it in the numerator, I'm going to put it out front. So we've got g of x plus h, and then times whatever's left over. So this is going to be f of x plus h minus f of x over h. And then we've got plus this limit over here. And again, we're going to factor out the thing that's in common. In this case, it's an f of x. I'm going to factor it out and actually bring it out front. And then what that leaves us with is g of x plus h minus g of x over h. So in each of these limits, we have a product of two things. And we know that when we have the limit of a product, we can rewrite that as the product of the limits. We can split this up into two different limits, so long as those limits all exist, which we'll see is the case later. So we can write this as the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of that fraction f of x plus h minus f of x over h. And then plus, we're going to do the same thing over here. We're going to separate the limit of a product into the product of limits. So we're going to write this as the limit of f of x times the limit as h approaches 0 of that fraction g of x plus h minus g of x over h. And I know it might seem, you might know exactly where this is going, but it might seem confusing. Why are we adding and subtracting in terms and splitting everything up and whatnot? But this actually puts things in a much better position for us to deal with. Now, we have the first limit as h approaches 0 of g of x plus h. Well, that's just going to be g of x, so long as this is a continuous function. And since we're assuming that both of these functions, f and g, are differentiable, that means that they are continuous. So the limit as h approaches 0 of g of x plus h is just going to be g of x. And then let's look at this other limit. This should be something that you recognize. The limit as h approaches 0 of f of x plus h minus f of x over h. This is something we've seen over and over and over again. This is the limit definition of the derivative of f of x. This is just f prime of x. And then we've got this plus over here. The limit of f of x as h approaches 0 is just f of x. There's no h in there. With respect to h, that's a constant, so the limit of that is just f of x. And then if we look at this other fraction over here, this is also a derivative. What is it the derivative of? It is the derivative of g. And I'm just going to take each of these two and rewrite the way that they are organized. I'm going to put the f prime out front. So this is f prime of x, g of x, and then plus g prime of x, f of x. And this is exactly what the product rule says. And so this is where the product rule comes from. It comes from looking at that limit definition of the derivative of that product of functions and separating things out and adding in this special version of 0 that allows us to break things up into two different parts and have each one of them pop out a derivative in the end. So whoever came up with this first, I think it was Leibniz, but I could be wrong. Whoever came up with this first, it was a lot of thought and work and effort that went into figuring out exactly what version of 0 we can add so that we can split things up and have some nice derivatives pop out. And it's far beyond what I would expect anyone in my class to be able to pull out of their hat on a test. This is not something I would ever test a student on, unless you were a very, very advanced math student. But I just wanted to show this so that you know exactly where the product rule comes from.